Alright, so today I'm gonna explaining this important paper with the title IS-GNN. Graph neural network enhanced by aggregating influential and structural similar nodes. This paper in 2024 in the Journal of Knowledge-Based Systems by China. Nowadays, it has been demonstrated that graph neural networks are a powerful tool for graph representation learning. However, most GNN models are shallow ones because stacking more layers causes the oversmoothing problem. In addition, the conventional neighborhood aggregation GNNs have an implicit homophily assumption, leading to poor performance when dealing. So this homophily is an heterophily problem. Definition is the thing that we have reviewed in the past 4 or 5 videos. To address the aforementioned issue, we present a new GNN model called IS-GNN to effectively enhance the representation quality of nodes in neural network. It learns the representation of each node using 3 aspects of information: local structural information, global topological information from influential nodes, and finally, homophilous information from its structurally similar nodes. So you see the framework. We have influential nodes, that these nodes are important, like if you do the scoring idea in hierarchical graph pooling. So the same tools and techniques can be used here. Also similar nodes, we can see the similarity of nodes using this matrix, and using these two, influential and similarity, then we can represent very good representations, and we will go through them. So from the point of view of network dynamics, influential nodes are widely scattered and is crucial in positioning in graph. Because in crucial positions in a graph, they say those nodes are very important. Because they are globally invariant, we identify a collection of influential nodes in advance using vote rank approach. Structurally similar nodes of different nodes are not the same. We need to compute the structurally similar nodes for each node. On this account, we first compute the similarity matrix of all nodes using the LRE algorithm. So we search the similar nodes of each node from the matrix, specifically a collection of nodes, where this similarity between nodes I and j is greater than a threshold. That threshold is epsilon. So it learns an embedding of each node according to influential nodes. Because the influential nodes are not variant for different nodes, we consider the distances of a node to the influential nodes. This is a very lovely idea, very deep idea, I can say, because all the idea of metric embedding, positional encoding, all of these things can be done very naturally, very intrinsically. So this Dij is the shortest path, shortest distance from node Vi to the influential node Vj. So this is their embedding. This is how we write the embedding. And Xj is just a raw feature of node Vj. But this distance is important, that in the denominator you see the shortest distance from node Vi to an influential node Vj. And we sum over influential nodes. And this component learns another embedding for each node from its structurally similar nodes. So the embedding of node V sub I from its similar nodes is computed like this. W2 is just another learnable weight. So the third embedding of each node is learned from its neighborhood. Even in a heterophilous graph, the neighborhood context plays a critical role when generating the representation of node. So we learn the third embedding of a node by means of its neighborhood information. We encode the information of a node and its neighbors separately to retain the original graph structure without introducing too much noise information of heterophilous neighbors. And finally, we just concatenate this neighborhood similarity and influential nodes here, those representations. We concatenate them so we have a final embedding. Then we give this final embedding to softmax. After multiplying by W, we give it to softmax. Then we can classify. So this is just a quick summary. Influential nodes here. We model similarity, ego, neighborhood because of the heterophily. And finally, we get this softmax to predict. And we return the labels of unlabeled nodes. So for Texas dataset, for Wisconsin datasets, you can see visualization of nodes on heterophilous networks. Also, they did experiments on other datasets like Chamelson, Actor, for node classification. So they compare even the simple MLP to their models, 7386. But from graph convolution, you have this comparison, graph attention, graph sage, so the result is here. These are for other datasets like Cora, CiteSeer, PubMed. So for Cora, they compare MLP with their model. They compare GCN, graph convolution, graph attention, graph sage. For example, graph sage is just 5% less than the result of their paper.